Hi everyone, if you're here today, you're probably looking for some guidance on endothermic and exothermic reactions. We're going to be looking at potential energy diagrams for these two types of reactions. Um, Chances are if you're in grade 12, first year university, or even grade 11, you're going to get a variation of this question. Either you're going to be asked to draw the graphs, or you're going to be asked to identify the graphs, or the graphs and the details are going to be used as cues and little clues for other more complex questions. So when we're thinking endothermic and exothermic, we want to think about heat being absorbed or heat being released. Okay? That's the main difference between these two types of reactions. All right? Heat absorbed, heat released. So let's take a look here at our endothermic reactions, okay? So we're going to start with endothermic. If you have an endothermic reaction, that means the heat is being absorbed in this type of reaction, okay? So your reactants are starting at a lower level of energy. They're absorbing heat and then producing your product, okay? So this is very important in terms of how we would place reactants and products on our graphs. As you see over here, you have the potential energy side of things on one axis, and then you have the reaction progress on the other axis. And so first step is to identify what type of reaction you have, endo, exo, and then where your reactants and products are sitting relative to one another on the potential energy axis, okay? So endothermic, it means that reactants are starting at a lower point. Products are starting at a high, the products are going to be, sorry, they're not sorry, products are going to be at a higher energy level, okay? So, sorry, just changing the color here. Okay, well, over here, we just looked at this. So we're going to put them on the potential energy axis. So this is very important. Marking where R is, marking where P is, reactants and products, what the delta H or change in enthalpy is, and also marking the activation energy. Okay, so these are some of the things that you want to make sure you can recognize and or draw on the graph. Okay, so endothermic reaction reactants higher. So we're gonna put the reactants lower. My apologies. And then products higher relative to one another. Beautiful. Step one done. Let's draw this reaction. So we're gonna just go. There you go. Okay. Wonderful. So for exothermic, we'll just be doing the same thing. We'll go over it, but it's just going to be different levels, okay? So first and foremost, let's look at the enthalpy or the heat, okay? So enthalpy for reactants, so the heat of the reactants. We can also interchangeably use the term energy. Sometimes I will use that because heat is, energy in the form of heat. So we're going to look at the change in enthalpy or delta H, okay? Whenever delta is somewhere, that's your cue. That's going to be a change or a difference, okay? And whenever you want to find the change in something, you're going to do the second point or the end point minus the beginning point. So you're going to draw a line from your reactants, just a straight line, just to be able to mark it on this side. And the space between your reactants and product is going to show delta H, the change in enthalpy, the amount of heat being absorbed throughout the progress or the process of this reaction, okay? So delta H is going to show your enthalpy change, okay? The peak point of this graph over here is going to be your transition state. Well, we know when a reaction is happening, the bonds within your reactant have to break and some new bonds need to be formed in order for you to have your product. So the transition state is where these bonds are being broken and bonds are being formed. It's very, very unstable, okay? So this is kind of if you're cooking, this is not the end product, but you're kind of starting to chop things up and mix things, and that's where you're at. Okay, so this is where bonds are being formed and broken. The space over here from the transition state to the energy of the reactant, that's going to be your activation energy. Okay, so that's the energy required to go from the reactants to that transition state. Okay, it's kind of like a barrier. Okay, so you have to break through that barrier. It's a standard. You have to have the activation energy in order for you to go past this point of the transition state and for your reaction to occur and for you to get to the products. Okay, so for you to get to your destination, which is your product, you need to have the activation energy required. Okay, and this is where we have that. This is how we show it. Okay, so it's the difference between the energy, the space between the energy of the reactants and the transition state. All right, now let's take a look at our question where we did one without. So this is without a catalyst. Okay, so now think about it this way. What would happen if I were to add a catalyst to this reaction, to this endothermic reaction? So how does a catalyst impact an endothermic reaction? Well, we know catalysts do have an impact, but it's limited to certain aspects of the reaction. So when you draw this, this is oops, okay, there you go. The lilac line shows our catalyzed reaction. Okay, so when you add catalyst, it helps you get from point A to point B. Okay, it will reduce that energy, the activation energy required for this reaction to occur. Okay, when you're drawing the catalyzed version, you want to make sure the peak is going to be lower, so the amount of activation energy required is going to be less, and you want to be able to show that on your graph. Okay, perfect. We're going to move on to the exothermic. So exothermic, that's your cue. Heat is being released, it's exiting. Okay, exo, released. Okay, so that means your reactant is going to start at a higher level of energy in relation to your products. Okay, wonderful. So I sound like I'm talking to myself. Okay, yeah, I'm so used to teaching students. I like to confirm. All right, placing our reactants and products on the graph. Reactants, not there. Let's put it a bit higher so I can show it better. Okay, so I'm going to put my reactant. Product is going to be lower than the reactant, okay? So let's just draw that, connect the two. There you go. That's your exothermic, okay? Now, same thing that we did. The process is the same. You're going to draw a line. Oh, sorry. You're going to draw a line from your reactant straight. And the space between that is going to be your delta H, change in enthalpy. Okay? So that will showcase your change in enthalpy. Now, pay close attention to this. So you have your line, the delta H for endothermic is above that line. The one for exothermic is below the line, okay? So just keep in mind that shows heat being released, okay? Delta, well, look at that. I just hit undo. Okay, delta H. Okay, there you go. Heat being released. Now, let's do the same thing with our activation energy and transition state peak point of my diagram. Bonds are being broken, new ones are being formed. Activation energy over here is going to be that little space between the potential energy of your reactants to that transition state, okay? So this is the minimum energy required for you to be able to break these bonds. Okay, now, important point. Even though this is exothermic, you still need activation energy, okay? That has nothing to do with the activation energy. You're still trying to break bonds and form new ones, so you still need activation energy. So the releasing or absorbing doesn't have really much to do with that. Same thing with the catalyst over here with the lilac line. I'm showcasing that my activation energy is going to be lower. So the impact of the addition of a catalyst to both an endothermic and exothermic reaction is the same. It lowers the activation energy. So there is no difference in how the catalyst affects your reaction. Okay? So that doesn't change. Now, couple of important points here. We want to go back to our delta H over here quickly. So the delta H is going to be, the amount of heat absorbed in our endothermic. So I'll just write endo here just to make things a bit quicker. So heat is absorbed. Now, the formula for delta H is, H of the product minus H of the reactant. So I also sometimes use, again, energy interchangeably because heat is energy in the form of heat. So you know that your reactants are going to be at a lower level. They're going to have a lower level of heat and your products are higher. So HP minus HR is going to give you a value that is greater than 0 because this is an endothermic reaction. So it's going to be, delta H is going to be positive. You have a larger number minus a smaller number. Okay? Great. For the exothermic one, the process is the same, formula is the same, concept is the same. However, we know that my reactants and my products are starting at different levels. All right? Heat is being released, so delta H shows how much heat is being released. Reactants are higher, products are lower. I'm not going to rewrite this, okay? So delta H is equal to HP minus HR. So that's for your product minus your reactants. Since you have a larger number here for your reactants being subtracted from a smaller number, then you will have a negative value. And going back to this, you can see delta H is above the line for endothermic and below. I just showed it with the laser. Okay, now I'm going to add a couple of final notes on this before the video ends, but two very, very crucial important points. Delta H is not affected by the addition of a catalyst. You're trying to go from Paris to Rome. Adding a catalyst is like how you're getting there. You're not changing your point A and point B. Your destination is not changing. It's just how you're getting there, how much energy you require to get there. That's what's changing, okay? So the change of enthalpy is going to stay constant even if you're adding a catalyst. However, it's the activation energy that is going to have an impact, okay? As you saw over here in these two. So reactant to product, you're going from point A to point B. No impact on delta H. So point A to point B doesn't really change your starting point and your destination. It does, however, change how much energy you require to get there, okay? So that's where my catalyst is going to help me out. All right. So this is another important point you want to remember. Also, these are all things that you can, you know, be asked in the format of a multiple choice question, or it can be a trick question, part of a bigger problem set. Okay, so these are two very important points that you need to remember. Now, let's do a little bit of a recap step by step of these sort of questions. Let me go down here. Actually, Let's see. We're just going to do never mind. Let me go up there. Actually, this might be easier to view, or take a screenshot if you want to. So step one, placing the reactant and product. So you want to make sure you get the placements correct. Step two is going to be the change in enthalpy, delta H. You want to mark that. That's going to be the space between the reactants and products, potential energy space between them. Number three, you want to mark the transition state. That's your peak point, okay? Right after that, you want to move on to showcasing your activation energy. And if your question gives you a catalyst or asks for a catalyst to be added, then you just show it with the catalyst, which is going to be the version in lilac, which has a lower activation energy. I hope you found this helpful. Like and subscribe for more. Have a good one and good luck. Bye-bye.